Hello, chemist. We have a couple more lectures on acids and bases and buffers. So we're trying to finish that up. Last time we spoke, we were talking about acids and bases and conjugate acids and bases, and we were talking about the equilibrium expression for a weak acid or base system. And so just kind of finishing that thought, if I write the Ka for this acid, this sort of generic acid that donates its hydrogen to water, and then that water accepts it and becomes hydronium, and then what's left over after the hydrogen gets donated is the conjugate base. When we write that equilibrium expression, we said we write the hydronium, the conjugate base, and the acid in that expression, and basically we leave out the water because it's a pure liquid. And so that becomes an interesting conversation when we start talking about water. So this word amphoteric, if you think about the word amphibian creatures live on both land and water. And so maybe you picked up as we were going forward that water can act both as an acid and as a base. And so if I write a reaction, this is sort of crazy, but if I write a reaction of water reacting with itself, and we just say, well, let's let this one be the acid and this one be the base, we know that the hydrogen gets donated by the acid to the base, and what I have left over is the conjugate base, the OH, once the hydrogen is donated to the other water, and I get my hydronium ion. Since both of these are liquids, both pure liquids, and these both are aqueous, right? If we put that back into this expression and we give it a special name, we'll call it Kw because it's the equilibrium of water, you'll see that we just have the products, hydronium and hydroxide multiplied together, and we leave out the liquid. And so this is the interesting basis for what you have probably heard of, which is the pH scale. So I'm going to kind of quick flip over there, and you may know about the pH scale. Basically, that means the power of the hydrogen ion. All right, and you may be familiar with this if you have a water system like an aquarium. You might have to worry about the pH. If you're a gardener, you worry about the alkalinity of the soil, acidity of the soil. And maybe you're familiar with the fact that when you have water, it's neutral, and this pH scale, as you go on the large end, the higher you go, the more basic the solution. And when you go down to the low end of this, you're more acidic. And I'm going to try to explain that. There's a couple, 3 formulas that put that all together mathematically for you. But basically, I just wanted to start off by talking about, well, where does that pH number, that scale from 0 to 14 come from? It turns out that when you look at a water, any sort of sample of water, you know that we have found that the concentration of that water is 1 times 10 to the negative 7th molar, or just 10 to the negative 7th molar. And it's true for the hydronium ion as well. The concentration of those two substances being equal is what actually makes this substance. When you have both hydronium and hydroxide, and you have equal amounts, that's what makes this system neutral, and we'll get to that in a second. But if I just write that again as 10 to the negative 7th, maybe some of you guys know your math in terms of exponents, that you add the exponents when you multiply them together, and so you get Kw is equal to 10 to the negative 14th. And there it is. So if you recognize that number right there, and you go back to the pH scale, that's kind of the reason why the scale goes up to 15. It has to do with the concentrations of the hydronium and the hydroxide in a neutral solution, in a water solution typically. So that is the basis for the pH scale. Now, it gets a little bit crazy. The basis for the pH scale, again, is this relationship between Kw, H3O plus, the hydrogen ion, and the hydroxide ion, where Kw is actually what we call a constant. It's 10 to the negative 14th molar. So you could, again, rewrite that as 10 to the negative 14th, because they say the same thing. This is a logarithmic scale, and that scares people but I just want to try to convince you that it's not so scary after all, because I think you know a little bit about inverse functions. You know that if I add x plus 4 to get 8, and I want to solve for x, most of you know that the inverse of addition is subtraction, and if I subtract 4 from both sides of the equation, I can figure out that x is 4. So subtraction is the inverse of addition. You know that. Okay, if I have 4 times x equals 8, you know that since these are multiplied by one another, you know that the inverse function of multiplication is division. So you'd divide both sides by 4 and you'd get an answer of 2. So you're probably, I know you're familiar with inverse functions, right? If I wanted to solve x squared is equal to 16, many of you guys know the inverse of square is taking the square root, and we could actually figure out the answer to this. And so again, basically exponent, so basically if we have a base and we have a power of, so the power itself is the variable. That's kind of a different scenario, and I just want you to note the difference, right? When we look at this, the base is the variable and the exponent is squared. Now this makes it totally different when the variable is the exponent. So we have a variable exponent. In order to undo that, in order to have the inverse of that, that's where the log function basically comes into play. Okay, again, some of you guys may have experienced this in a math class. Some of you, maybe it's been a long time, but that's the basis of this pH scale. Okay. Again, you probably, when you talked about logs, you probably talked about the decibel scale, which is the sound, not decimal, but decibel scale, decibels scale. Some of you probably talked about the Richter scale. I think it's ER. And then you probably at that time talked about, you probably talked about the pH, right? So, because those are the famous logarithmic scales, and basically every time you go up by a power 10. So it goes up 1, and then 10, and then 100, and then 1,000, and then 10,000. So that's how this scale works, okay? So that's the reason, and so the fear is when you look at the equations, they look pretty scary. So I'm going to just show you the two equations. So pH being the negative log of the hydronium ion concentration, and what I just want to tell you is when you look at the hydronium ion concentration, 10 to the negative 7th is equal to the concentration of hydronium, for instance. Basically what I want you to see is that you have this negative exponent, right? So the negative undoes the exponent and makes it positive. And then the log basically takes that number and puts it down into a number. So when I have an H3O plus concentration, that's 10 to the negative 7th, if you actually put that in your calculator and take the negative log of it, you're going to get 7. And that's basically what we see when we see the pH of 7 on here. That's what it means. It means that the H3O plus concentration, we can just write it. I keep putting the 1 in front, but you could just write it as 10 to the negative 7th. And so that implies that 10 to the negative 8th and 10 to the negative 9th are the concentrations of these guys here. 10 to the negative 6th is the concentration of the milk. And that's the hydrogen or the hydronium ion concentration. Okay. pH problems come in, so two flavors. You have the log. So this one is when you're basically given the concentration of the H3O plus, right? So this is when you know the concentration of the H3O plus, then you can tell me what the pH of the system is. But if you have the pH, right, if you're given the pH, you can use sort of the inverse function of that to determine the concentration of the H3O plus. They are related by this exponential log relationship. Okay, and we're going to do some problems with that. And so basically in tandem with this equation, which we already derived, those are the three equations that help you solve any pH problem. Okay, and we're going to get to that in a second. So what I first want to do is try to establish just an understanding of what it is when you have a neutral solution, an acidic solution, or a basic solution. So when we talk about pH of a neutral solution, perhaps you know, right, the neutral solution, it's right here, it's in the middle. So the pH is equal to 7. That's what it means to be neutral. And what else it means to be neutral is the OH concentration, the base concentration, is equal to the acidic concentration. So H3O plus hydronium and hydroxide concentrations are equal, and we know what their value is. It's 1 times 10 to the negative 7th molar, and that looks really ugly. So you could write it, if you want, is just 10 to the negative 7th. So they're both equal. That's what makes it neutral. There's equal amounts of acid and equal amounts of base, and they neutralize each other. Okay. So what happens when I have an acid? Well, that means the pH is less than 7. I'm down here in this range down here. This is the acidic range, right? And that we go down in numbers, and that's because the concentration of the H3O plus is larger. So we've got the situation where we've got a larger amount of H3O plus in the solution. So when we have more acid in the solution, it's deemed acidic, right? And so that means that the concentration of H3O plus is greater than 1 times 10 to the negative 7th. Now that seems really weird, but I want you to recognize that 10 to the negative 6 is larger than negative 7, right? Those are those negative exponents that make you confused, but you're getting closer to 0. You're moving up towards the positive end of the number line, if you will, right? And then the OH minus concentration must be less than 10 times 10, 1 times 10 to the negative 7th. So there's a lot of hydronium and not so much hydroxide. So lots of hydronium or lots of hydrogen ion, less OH minus. Okay, so when we talk about a basic solution, essentially everything's the opposite. pH is greater than 7, and that seems weird, but again, we want to recognize that 10 to the negative 8th, for instance, right here, that concentration is lower. The H3O plus concentration is lower. That number is farther from 0. It's more negative. It's a smaller number, right? And it's weird in your head if that doesn't make sense. So basically, when we have a basic solution, I always kind of laugh at myself for using that word a lot when I'm talking about acids and bases. So what we have here is the H3O plus concentration is less than the OH minus. So in that sort of relationship of these guys right here, if the H3O goes up, the OH minus has to go down. And then the opposite's true. If this goes up, then this has to go down because this value is constant. So they are inversely related. Okay, so basically the OH minus concentration is larger than 1 times 10 to the negative 7th, and the H3O plus concentration is less than 1 times 10 to the negative 7th. You'll notice that those inequalities just switch sides, right? So basically you have lots of OH and very little H3O plus. So less, that's whatever I canceled there. So lots of OH minus and less H3O plus. That's what makes a solution basic, okay? So that's the basics of the solution. That's the basics of the formulas that we need. And so how do we use those formulas? So that's what I want to show you in the next couple of examples, and then I'm going to have you guys practice, okay? So when we do these problems, again, it's kind of hard if you've never seen this before. It's really intimidating, but we know this is a urine sample. It has a pH of 5.9, and it wants us to calculate the H3O plus and the OH minus. So my first ask for you guys is just to think about this. Is this an acidic solution or a basic solution? The pH is 5.9, which is somewhere right in here. That's on the acidic end of the pH scale. So basically we know this is an acidic solution, okay? So then we know that, well, when we calculate the H3O plus and the OH minus, the H3O plus should be larger, okay? So how do we get to the H3O plus? Well, remember that we have a couple other formulas. We have pH is the negative log of the H3O plus concentration, and that formula is the inverse of this formula. 10 to the negative pH is equal to the H3O plus concentration. And so since we have pH, this is the better version. This is the better version of the equation to use because we're given the pH and we just raise 10 to that negative power, and then we get the H3O plus concentration. So we're gonna basically take 10 to the negative 5.9. And when we do that, we're gonna get a value. So on my calculator, I'm gonna do that for you. 10 raised to the, whoops. We're gonna do 10 raised to the negative, whoops. Let's try that again. So 10 to the 5.9. So let's try it on here. Where's my calculator? Math. There it is. So let's see if this works. We're going to take 10 and we're going to raise it to the negative, there it is, to the negative 5.9. So that should work. Okay, so our answer is 1.26 times 10 to the 1, 2, 3, 4, 5, 6, the negative 6. 1.26, so let's put that in there. Let's see. So the concentration is 1.26 times 10 to the negative 6, and this is a concentration, molar, okay? So basically that's the concentration of the H3O plus. Okay, sorry that took so long. So what makes sense in my head is that this exponent is really close to this one, and that makes me know that this is the right answer, okay? So the second step of this process is we have to calculate the OH minus concentration, and that's when we use this equation right here. We know that as the H3O plus concentration goes up, the OH concentration has to go down, and always those exponents have to be about 14. So I'm looking at that. I'm looking at that exponent, and I know my exponent on my OH minus concentration is going to be somewhere around -8, because -8 plus -6 make a -14. So I'm going to solve that for you as well. So this is our equation. We're going to go 10 to the negative 14th is equal to the H3O plus concentration times the OH minus concentration. We're trying to find this right here. We know that this value goes right in here. So we're going to basically, mathematically, take 10 to the negative 14th is equal to 1.26 times 10 to the negative 6. And we're going to solve for x, okay? And again, we can anticipate the 10 to the negative 8 is going to be somewhere close to our answer, okay? So mathematically, we're going to take, we're going to go back to our calculator. It took me a really long time to find it last time. Maybe I can be faster. There it is. Okay. So we're going to take that answer, and I'm going to take 10 raised to the negative 14th, negative 14, and I'm going to divide it by the answer I just got. We'll see if that works. Let's see. I don't want that to look like that. So I'm going to go over one. Whoops. Let's try that again. 10 raised to the negative 14th. I'm going to step over, and that's divided by the answer. Okay, and so then we should get, something close to -9. So I'm going to write down 7.92 times 10 to the negative 9th. Okay, that's a big number. One more time, I have to look at that. One more time, I have to look at that. 7.94 times 10 to the negative 9th. So our answer is 7.94 times 10 to the negative 9th. 7.94 times 10 to the negative 9th. And that's our OH minus concentration, right? So big question, just answering this question, thinking this through. This is our concentration of our our hydronium, H3O plus. This is our concentration of our OH minus. We've decided that this is an acidic solution because the pH is down here on the acid end, right? So the acidic end right here. So the question is this number larger than this one? So is the H3O plus concentration larger than the OH minus? And the answer is yes. Just a check here, just making sure that this number exponent and that number exponent add up to about -14, and they do. They're about -15. And the reason they're not perfect, they don't exactly add up perfectly, is because we have these coefficients out here in the front, and that's okay. So the math on this is a bit tricky, but that's always a way to check it, to make sure that your exponents about add up to -14, especially if you have coefficients in your scientific notation. Okay, I'm going to let you guys do this one, and we're going to go on to another problem, but I will put those in your notes when I upload it to Canvas. Okay. So it says, let's try this one. That's also a pH problem. I want to do one where we're doing the concentration and we're deciding the pH. Okay. So you should be able to do this one too. I will actually put that in notes. This is exactly like the previous one. Okay. This one asks us to calculate the OH minus given the concentration of the H3O plus. And then I'm going to add in here, I want you to calculate the pH too. All right. So again, remember there are only three equations, right? There's pH is equal to the negative log of the H3O plus concentration. So this one is given H3O plus and solve for pH. Okay. There's 10 to the negative pH is equal to the H3O plus concentration. That one is if you're given the pH, this gets us, you can solve for the H3O plus. And then the last one is 10 to the negative 14th is equal to H3O plus and OH minus. Okay, so usually what will happen is you'll need to use one of these and then you'll have to plug it into this one to get the other kind of variable. All right, so there's only really three variables in pH problems: pH, H3O plus, and OH minus. This first one is not too bad. It's asking us, it's giving, we're given the H3O plus, so this is the pH is, no it's not. It's 10 to the 14th. 10 to the negative 14th is equal to H3O plus times OH minus. And in all of these, we're solving for the OH minus. So 10 to the negative 14th is equal to 10 to the negative 8th times X. Again, this one's pretty basic because it doesn't have any coefficients. So we basically know this, that exponent has, and plus whatever's here, has to add up to negative 14. So we already know the answer because you can do that in your head. This is 10 to the negative 6. So the H3O plus concentration is 10 to the negative 8th. The OH minus concentration is 10 to the negative 6th. If I asked you to find the pH of this solution, you also don't need to do any math if you understand the concept, because remember, this is the negative log of the H3O plus concentration, right? The H3O plus concentration is 10 to the negative 8th. And so basically, I don't have to do any math. I just know the pH is equal to 8. So when there's no coefficient out there, you get to just kind of do that stuff in your head. So that's not so bad. I'm going to have you do this one. And I'll do one of these other ones down here. So basically, this one, let's solve for the OH minus concentration. So if I do D here, I know that 10 to the negative 14th is equal to the H3O plus concentration times the OH minus concentration. The H3O plus concentration, I'm just going to put it in here, is 2.5 times 10 to the negative 11th. And this is 10 to the negative 14th. And then this is just X. So just off the top of my head, I'm just going to give myself a ballpark figure. I know that this number should be somewhere like 10 to the negative 3rd. And the reason I know that is because negative 11 and negative 3 equal negative 14. It's not going to be exact because I have this coefficient out front. So I am going to plug this one in. So basically my math becomes 10 to the negative 14th. Right? And I'm dividing by 2.5 times 10 to the negative 11th to solve for X. Okay, 2.5 times 10 to the negative 11th. So I'm going to take 10 raised to the negative 14th power, and I'm going to divide that by, I have to check my work again. Let's see, 2.5 times 10 to the negative 11th. Okay, so 2.5, I'm using the exponent button here to the negative 11th, right? And then I get 4 times 10 to the negative 4th. So let's put that down, 4 times 10 to the negative 4th. So my, in this problem, my OH concentration is 4 times 10 to the negative 4th molar. Again, we're asking ourselves the question, is this an acidic or a basic solution? And if I look at that number and I look at that number, I see that I have a lot more OH, right? And I see, in this, I can just see the pH of the system, okay, is about negative 11. And so that's a basic solution. Okay, So hopefully that gives you a little bit to work with. I'm going to ask you to solve B and C. I will put that in your notes. I'm going to ask you to solve that one and this one here, and that'll give you some practice, and I can get those answers up for you. Okay, thank you so much for listening. I hope you're having a great day.